Okay, welcome to this presentation on Statistical Quantification of Differential Privacy. Thank you for joining me. So, as David has just told you, so this is joint work with Önder, Askin and Holger Dette, which are colleagues of mine, all at the Ruhr-University, Bochum, Germany. And since this is the first talk in the session on differential privacy, I think it's nice to just say in one word what differential privacy is all about. So, situations where we're interested in differential privacy arise in the following situations. So we consider a number of individuals which have data which is collected in a database which we call X. And we're interested in publishing a query of this database, say, for example, in very simple case, the mean of the database, right? In situations where we want to publish this kind of query, there's a danger of impinging on the privacy of the individuals because there might be an attacker who's really able to infer data of the individuals or participation of individuals by virtue of this query. So later on, I think we're going to look at an example of this from the US Census. So this is a real concern when you want to publish data. Now, the insight of differential privacy is that you can somehow protect people's privacy by adding random noise basically to the query. And the idea now is that if you add a sufficient amount of noise, this will actually mask the individual and small contribution of any participant in this database. What you wind up with is an output which is distributed according to A of X, where A is a randomized algorithm. So you're going to have an output which follows a random distribution. In differential privacy, we'd like to think about situations where we have one individual in a database and want to grant it plausible deniability. So we look at this orange individual in the database X and exchange it with another individual, the blue one, in the database X prime. In each case, A of X is going to follow a random distribution. And now differential privacy says, well, you know, privacy is protected if these two distributions are in some suitable sense similar. And this makes sense from an intuitive viewpoint because if the attacker is really not able to tell whether the output is generated by A of X or A of X prime, this really grants plausible deniability to each individual. Now let us look at this from a more mathematical perspective. Differential privacy is a quantitative notion, and it is quantified by a privacy parameter epsilon. And epsilon lives on the positive real numbers. Somewhat unintuitively, or at least that's my opinion, small epsilon stand for high privacy, high epsilon stand for low privacy. I always try to imagine this as being like epsilon stands for the amount of information that is leaked. So you basically have small leakage, high privacy. So for the purpose of this talk, I think it's really fine to think as small epsilons as the good ones, which protect privacy, and large epsilons as being the bad ones. It's not that simple, but I think for us today, this should be fine. When you construct an algorithm, you usually want to determine its privacy parameter, and usually when you design the algorithm, you're going to do this by formal mathematical proofs. This is the case when you design the algorithm yourself or when you have access to the source code. However, today, I want to talk about the situation when this is not so, when you're looking at the algorithm as a black box. If you don't have access to the algorithm, you are really reliant on the outputs of the algorithm if you want to say anything about its privacy. These kinds of situations might arise, for example, if the algorithm is owned by a third party and you may privatize stuff by it, but they're not willing to share the code, or it might be even if the code is yours, but it's really kind of complicated, and you want to check whether you've made any mistake in there. And so it might be easiest to just, look at the outputs. How do you do this? Well, the standard approach in the literature, so there's literature on anything, so there's also literature on privacy testing. And the way you do this is you develop another algorithm N, you feed outputs of algorithm A in M, and M outputs a lower bound of privacy. For conceptual reasons, it's usually not possible to give an upper bound, but only to give lower bounds. We'll see this in just a second. This lower bound is based on random outputs of A. This means that it is itself random, but it will hold with high probability if you design it correctly. So this lower bound has the advantage of, if you do it cleverly, it will approximate epsilon. It will tell you that the algorithm is not more private than this lower bound LB. And it might even serve to as it might help you to expose faulty algorithms. So the owner of the algorithm says, well, this is an epsilon differentially private algorithm, isn't this superb? And you say, well, you know what? The lower bound LB states that it is larger than the claimed privacy level epsilon, so there might be something fishy about this algorithm. So the way you get these kinds of lower bounds is usually the following. You look at a kind of privacy loss function, and I will not describe yet now each and every detail of this rather technical object, but you know, it's quite easy to get the gist of it. You look at the probability of A of x doing something, compare it to the probability that A of x prime is doing something, and if they're basically doing the same way, you have privacy. If they're doing something very different, you'll have high privacy violations. The inputs of this function are x, x prime, so you have these adjacent databases where you have switched one individual for another one and going from x to x prime, and you have an input, a set E, which is the input of this loss, and this basically consists of potential outputs of the algorithm A. So think about an interval or two intervals, and 12 points. There are really a lot of possibilities here. Differential privacy can now be defined in terms of this loss function as the maximum over all adjacent databases x, x prime, and over all measurable sets E. Now this gives you, when you think about it, kind of a nice way to come up with lower bounds. You can just shove in a bunch of these triplets, x, x prime, E in there, and you know, some of these are going to be closer to epsilon, some of them are not, but you're just going to take the largest one. Voila. Now, when you think about it just for one more second, you'll realize that we usually do not have access in a black box scenario to LXX primes, to this loss function, so we have to estimate it. And this is basically what people do in the related literature, so let me give you one. It is admittedly simplified, but this is how people look at this. So they propose an algorithm M, and this consists of two blocks. In the first one, you approximate instances of Lx x prime of E, and the second one you maximize. Admittedly, the first one is usually the more interesting one, and we're going to focus on this now. So there are two steps, basically. You have to come up with reasonable databases, xx prime. This step is usually the easier one. So there are good heuristics. They have to be far apart in some sense, and this is usually not a problem. But the whole issue of estimating LXX prime becomes more difficult. So what you have to do is you have to rely on outputs of the algorithm A of x prime. So these are labeled x1 up to xn and yn up to yn. You have this, I should notice, is what really drives the runtime, because you have to generate these samples. If the samples have to be large, you have a lot of runtime, and you won't believe it. If they're small, there's less runtime. You have to compute empirical probabilities. Notice that LXX prime involves probabilities. And people use these empirical probabilities most of the time. And yeah, I mean, they are quite straightforward. You count the number of x's which are in E, and you divide by the total number. This is the empirical probability. Finally, you have to choose the event E, and this is really a tricky question, because when you think about it, the space of possible events is really large. I mean, even if the algorithm just has D outputs, the output space is going to contain 2 to the D outputs, and they can just look pretty crazy. So coming up with a reasonable event is difficult. Coming up with a reasonable event is difficult. So current research focuses on machine learning classifiers, but this still needs additional sampling. In our work, we improved this method by avoiding the process of event selection. We did this by adjusting the estimators of the probabilities, and finally, we're able to reduce the sample sizes. Let me do this real quick. So what did we do? We focused on the probability densities of the output algorithms. The nice thing about the probability densities is these are real valued functions. You can actually draw them. And you can actually draw this real valued loss, which compares the two densities. Everyone who has ever worked with differential privacy knows that differential privacy is really something about the ratio of densities, and this is basically included in this loss function here, implicitly. Now, the differential privacy parameter can also be understood as the maximization of this real valued loss. And this is a simple insight, but it leads you to another and perhaps easier solution of this difficult problem. What we've done as a consequence is the following. We've said, okay, we're going to base our estimators, we're going to estimate this real valued loss function by estimating the densities. There are some standard density estimators, which are, I call them glorified histograms. They're called kernel density estimators. They're basically smoothed histograms. You see a kind of wacky version here. The red one is estimating the blue one. They get much better, much faster. And then you can just estimate this this loss function. You can estimate it, you can maximize the empirical loss, and you know what? That's actually it. This is how simple this goes. Now, admittedly, when you, at the end of the day, want to prove this high probability statistical bounds, there is really some mathematical work behind the scenes going on, but still, I mean, the intuition is rather simple. Finally, let me summarize what the improvements were compared with previous works. We were able to substantially reduce the complexity of the problem. And reduce the complexity of the problem in terms of sample size. We derived quite tight lower bounds. So if you want to have a look at the simulation, they're not completely trivial, so have a look at the paper. But we used sample size like 2.3% to 3% of the previous works and still derived quite tight lower bounds. So this means that this program runs really fast. You can run it on your desktop computer. You don't need a server or something. So this is nice about it. You can just easily implement it. Because it relies on kernel density estimators, they're available everywhere. They're available in R, in Python. You don't have to implement them or something. It's just super easy. Finally, we also were able to derive theoretical guarantees, and I think this is kind of nice. When you know basically that your lower bounds really converges and converges at a certain rate. And these theoretical guarantees were, in my opinion at least, a good deal stronger than the related literature, where you usually couldn't prove rigorously that they converge. So this is basically where the mathematical theory kicks in. So in the words of a colleague of mine, this shows perhaps that the easiest way is not always the worst. Thank you very much.
Great. So we have time for a couple questions. So if you have questions, please step up to the podium and ask there, please.
Yeah, so I'm curious about whether or not your technique here would be extra powerful in a gray box setting where you don't necessarily know what the parameters of the distribution that the algorithm implements are, but you know that the algorithm's output is drawn from one of a family of distributions. You know, you looked at the code and you know there's like a little plus distribution in there. Could you use that to get better estimates of the density?
So do I understand you correctly when I don't know basically that it comes from a family, right? This is the question?
No, when you do, when you know that the
Oh, absolutely.
Yeah.
So this would make actually a lot of sense. We've also thought about this because I think this is a natural question to ask if you basically say, okay, there's a parametric model underlying it,
yeah.
and then perhaps I can estimate at square root n rate, which is faster than the non-parametric rates that we have derived. I certainly do believe that this is possible, and you can adapt it quite easily, but I think this would be desirable, right, if you know it, and perhaps if it's your own algorithm, you know it, right?
Yeah.
And so I think this is a very good question. Thank you.
Cool.
Please.
Okay, thank you. If the algorithm A of x is producing a real number and is trying to hide a covert channel in the very last few digits of A of x, say to hide the encryption of x, I don't think that the estimator for the probability density will see that there is a covert channel here. And nevertheless, there will not be privacy at all, right?
I'm quite sorry. I should admit I'm not the original speaker for this talk. I'm just a mathematician, so you can explain it to me afterwards. But okay. I'm not quite sure, so I can ask out my co-author, who perhaps can answer this in a better way. I'm quite sorry for this.
Okay.
But we can definitely talk afterwards. Perhaps I can still understand it. Sorry.
Okay, thank you for your presentation. It was really informative. I had one question. You said that you can sample things from a distribution.
Yeah.
And you mentioned the numbers 2.3 to 3%, which of course looks impressive. But the question is that how does the effectiveness of your method really improve or depend on this percentage? And also, what number does this percentage actually entail?
So you mean the sample reduction?
Yes.
What is it?
Yes.
Okay, this is an excellent question, of course. I think it's of course kind of hard to compare this when I just say, the bounds are tight, we have used less sample size, right? I think our bounds are quite reasonably tight, which you can see in the paper. We've also tried to, in non-reported simulations, we've compared it to state-of-the-art alternatives, and we've tried to apply them with our smaller sample size, and there they performed really poorly. So I think that our method might be just very attractive for a small sample size because the other methods, the alternatives, seem to break down really for small sample sizes. And so it was really, we really thought about this as, can you implement it on a desktop computer or not? Perhaps this is a weird criterion, but at least it was, I think, motivated for users.
Okay, thank you for that reply. I think mentioning that you want to implement this on a desktop computer gives an even better indication of how good it really works.
Yeah, I mean, so we have access, of course, to desktop computers and servers, but I like my desktop computer, so perhaps this is just a personal preference of me. Okay, thank you very much.
Great. So if there are no other questions, let's thank the speaker again.